Hey, Sam.
Okay,
All
good.
yours.
Okay, great. Well, welcome to this CSRC colloquium. We're very pleased today to have Professor Kevin Johnson to present us today a huge problem for big data. And yet he's going to talk about what the metrics of billions order. Professor Johnson received a PhD from University of Washington and was postdoc at Caltech and other places. And he is maintaining a very active group, and he is now supported by 5 grants. He has many students, and 3 of his students made presentations at CSRC Access, excellent presentations, and talk about how to compute huge metrics. That method and the discussion actually inspired me, and I benefited a lot. So what today we'd like to hear from Professor Johnson, this new method. Kevin.
Thank you. I mean, some of these methods actually isn't really completely new. Many of it goes back a long time, but it, in the words of Shakespeare, it may be new to you, to some of you. But also, I should emphasize that if you read applied physics papers or applied math papers on some of these topics, they'll do a demonstration project of that, 100,000, dimension 100,000 or dimension 1,000,000, and that's just peanuts for what we're interested in doing. So let me talk about what I'm going to talk about today. I'll start by laying the scientific context, and one of the themes I want to talk about is knowing the context is important, which of course is the whole theme of the computational science program, that you can't actually really solve problems very well computationally or mathematically unless you understand the context. And what we need are low-lying eigenpairs, eigenvalues, and eigenvectors of very large, although it turns out very sparse matrices. And then I want to have what I call 4 different voices in the algorithm, 4 different sort of views of it. We'll talk about from the viewpoint of the matrix. We'll talk about the choice of our basis states that we're calculating, and it can make a big difference. We'll talk about the physics, which will actually give us some clues as to how to efficiently represent the matrix elements itself. And then finally, it's important to know how computers work, and you can find that you can, if you understand how a computer works, you can actually design an algorithm that will speed you up tremendously. So those are all topics I'm going to be talking about. And let me point out this idea that black box algorithms are not enough. Context matters. You really have to, I believe you have to understand the problem to really design a right algorithm. So let me first start by talking about the scientific context, why we have to worry about very large and very sparse matrices, and give you an idea of some of the issues that we deal with. So we need to solve a large eigenvalue problem. It's going to be the nuclear many-body problem, quantum mechanical one. And we use what's called an occupation representation for a physical basis. I'm just going to skim over that, but it does have some relevance. So what we're doing is we're solving for the structure of atomic nuclei, not just the ground state, the Grundstück, the lowest state, but also excited states. And we're going to use a time-independent Schrödinger equation, which, to us just looks like a differential equation. Oops, I'm sorry about that. Hit the wrong button. A differential equation, but this kind of differential equation is too difficult to solve directly. So we write it as a matrix eigenvalue problem. And the way we do that is to just expand in some basis. This is a typical way one can solve these kind of problems. So we're going to do it, and I'm going to occasionally use the Dirac notation, which is here, but it's not that important for the problem we're going to be talking about. And like I said, we expand a basis to make this a matrix equation. And so again, using the Dirac notation, the things we need to know are these matrix elements of the operator. This is the Hamiltonian, but represented in some basis. And then we solve it an eigenvalue problem. Now for this, the matrix is going to be a Hermitian matrix, usually a real symmetric matrix. So it's going to have real eigenvalues and orthogonal eigenvectors. And how to calculate this matrix element and how to efficiently calculate will be key questions. And when you start to think about this, when you have very large dimension spaces, there's going to be a lot of these matrix elements. So to give you a sense of the size of the problem, let me give you sort of a tasting menu of the dimensionalities we face. And I put down some isotope, but you don't have to worry about them. And there's some information about the model spaces, but you don't have to worry about that. If we work in a dimension, say, less than 100,000, you can literally do this in under a minute on a laptop, at least the low-line eigenstates. If you do get something larger, a few million, it may be 10 minutes. If it's 100 million, if you have a modest workstation, you can do it in a few hours. If it's a billion, you could do it one day on an advanced workstation. Actually, earlier this week, I was solving for 2 states in a problem with dimension 2.3 billion on my advanced workstation, and it did it in less than a day. And then finally, if you get up to 2 billion, it takes maybe an hour on a supercomputer. And I've been running several hundred hours on supercomputers at Los Alamos earlier this week. But it's easy to get to spaces that you go beyond that. Again, here's a slightly different region of the isotopes, where you maybe start with 13 million, but you go up to 9.3 billion. I've done this in a supercomputer, but you can go to something that's slightly heavier, and the dimension would be 50 billion. And I haven't tried it because I don't think I really have enough computer time allotted to me to do that. So it's easy to think of problems that are too large, but this gives you a sense of the scale that we're worried about. And here's a bunch of other ones. This is looking at light nucleus carbon-12, but going up to large model space, again, going up to, say, 80 billion. We can do 7.8 billion, but 80 billion is just at the edge. The largest no calculation I know of is a dimension about 25 billion, done by Christian Forsen at Chalmers University in Gothenburg in Sweden. Now, one thing about these matrices is they're very sparse. So even in the small dimensional cases, the sparsity is about 10%. That means only 1 out of every 10 of the matrix elements is non-zero. And actually, as you get larger, they become more sparse. And one can understand that, although I'm not going to have time to delve into all the reasons why. But even with the sparse matrices, it's going to be a lot of data. So here's a case which is of dimension 500 million. If you take even just 0.2%, 0.002%, there's just 2 out of every million out of 500 million, 500 million. That still corresponds to 2 terabytes of data just for the non-zero matrix elements of these very, very sparse matrices. And here's a bunch of other examples. And you can see for these large dimension problems, and these are still very sparse, but you still have hundreds, if not hundreds of gigabytes, if not terabytes of data that you'd have to store just to store the non-zero matrix elements. Now, in old codes, when I was starting out way back in the dark ages, when we wrote, our Fortran codes in cuneiform, we would store the codes on matrix elements in disk and read them, and then from disk and process them. That's way too slow. Modern chips way outstrip I/O bottlenecks. So modern codes will store these non-zero matrix elements directly in RAM, but because this is so much data, you still have to do it across many, many nodes, and you have to use a supercomputer using MPI, message passing interface, for parallelism. So to summarize, we often deal with matrix eigenvalue problem with a very large dimension basis, and even though they're very sparse, even storing these non-zero matrix elements is a significant problem. Now, again, going back to the question, how do you find millions or billions of eigenvalues? Well, we don't. We're interested in the low-lying spectra you can measure. And so that's usually just a few extremal states, low-lying states, typically 5 to 10, although the exact number can depend upon the research. You might need just 1 or 2. You might need several dozen or a few hundred. It depends on the exact circumstances. And the standard solver for this is Householder, which is very efficient, and you can use LawPack routines in Fortran that will fully solve these up to about dimension 10,000 or so. But the work goes like the cube of the dimensionality. So every time you double it, the amount of time it takes goes up by a factor of 8. If you take a factor of 10, then it takes 1,000 times longer. So we want to we don't need all the eigenvalues. We don't really want all the eigenvalues. So we go to a different approach, the Lanchus algorithm, which goes back to the great mathematician Cornelius Lanchus. And so I'm going to talk about this from the viewpoint of how we solve matrices. And the way it basically works is you start from some initial vector. You seed it with some initial vector, which is called the pivot. And then what you do is you take your matrix. Here I wrote as A, but usually it's H. And when you apply this matrix and multiply times this vector, you get some other vector out. And just naturally, that vector is going to have some component that's parallel to the original vector, and then something that's perpendicular. So you've actually made a new orthogonal vector, which you can then normalize. Then you hit the apply that matrix to that second vector, and again you get some mixture of things that are parallel to what you already have, and then get a new vector out. And you just keep repeating this. Because of symmetry, you can show that some of these should be 0. But each time you iterate it, you're going to generate a new vector. And this is creating what's called a Krylov subspace. If you want to impress some of your friends, you call it a Krylov subspace. And this is a special case of what are called Arnoldi methods. These methods for generating basically iteratively some subspace and making it larger and larger. And when you do this, you get the matrix into a new basis, and in this new basis, the matrix is now tridiagonal. Actually, I've not been consistent. I called it A, but here I'm using H. But it's basically a matrix, and it's symmetric, and so it's like this. Householder does this too, but it does it for the whole space. But in the Lanchus algorithm, you do not fully transform the matrix. You just do this partially. But it turns out, and here's the thing that at first seems miraculous, but I'll point out that it's not. The extremal eigenvalues of this transform matrix, even when you truncate it, will quickly converge to the extremal eigenvalues of the original matrix. And so this is actually quite a powerful thing. And here's an example of this. This where is a function of energy and the number of iterations. So here's 10 iterations, 20, 30. So we created 30 vectors here. Out here, you've created 100 vectors, but this original space is going to be in the dimensions of thousands. So this is some subspace that's basically 100, and you have a matrix that's 100 by 100, which is an approximation to the original matrix, which was maybe several thousand by several thousand. These are the eigenvalues of that truncated matrix, and as you add more vectors, the eigenvalues come down, and eventually they converge to the extremal eigenvalues of your original matrix. And we can see these dots represent that. And so what happens is with more iterations, more eigenvectors will converge. And you basically do this until you have the number of eigenvectors that you want. And this was introduced by Whitehead, not quite, over 40 years ago in nuclear physics. Now there's a drawback, which is why you don't use Lanchus for everything, is there's round-off error, which causes these Lanchus vectors to become lose orthogonality, and you have to enforce that specifically. And that's a whole nother research area. Now we can ask, why does it work so well? And it has to do with moments. The basic chess move in this is you take the vector, you multiply your matrix time, and you get another vector. And that's the one you then find parallel and perpendicular components. But if you think about this in terms of what's called a spectral decomposition, now this has nothing to do with Ghostbusters, but it's an expansion into an eigenbasis. Oops, sorry about that. Eigenbasis. And so then you have the eigenpairs. Now you don't actually need to know this. This is just how we analyze it. You could expand the vector into the eigenbasis, and every time you apply the Hamiltonian, you're going to pick up an additional weighting of the eigenvalue. And you keep doing this. Now, when you've done this multiple times, say n times, you will get n powers of those eigenvalues. And this means that the extremal eigenvalues, the ones that are at either end, will get amplified, even if these weightings are small. And you can take the inner product with the original vector, and then you get basically something like this, which is some linear combination of the powers of the eigenvalue. And people have analyzed this in terms of a thing called the classical moment problem. It's basically you have a bunch of weights. Here, the weights represent these squared amplitudes, and then the distances are essentially the eigenvalues. And the extremal eigenvalues have a long lever arm. So even if there's a small weight, because it's a long lever arm, it has a big influence on this whole thing. And it turns out they're easiest to extract. You can show that, and by letting the matrix itself choose a Krylov space, it builds its own moments. And after n iterations, the truncated matrix has the same first 2n moments as the full matrix. It doesn't have all the moments, but the first 2n moments are the same. And because those, the only way to reproduce those moments is to reproduce the extremal eigenvalues. So in this way, you can understand why Lanchus works. Now, there's more to it than just that. We're not actually computing moments. The moment problem is actually famously, ill-conditioned, whereas Lanchus is not ill-conditioned. And then it has to do with the fact that we put this in terms of a tridiagonal matrix, which is related to the theory of orthogonal polynomials and much beautiful mathematics. If you go to national labs, talk to the applied math people there, many of them did their thesis on some variant of the Lanchus problem. So we reproduce these using an extreme O eigenvalue. This is why Lanchus is so efficient at getting extreme O eigenvalues. But there's still a problem. We have these huge matrices. And one question we can ask is, does it need to really be that huge? Could we choose some other basis which might be better? And let me give you an example, but here's where we sometimes have to make a choice in terms of efficiency versus simplicity. So like I said, let's dig a little bit under the hood of how we do these calculations. We're expanding in some basis, but now we have to ask, well, what are we using for this many-body basis? What do we use for the basis states? And what we're going to use is something called the shell model. This is Maria Mayer, who won the Nobel Prize for being one of the people who introduced the nuclear shell model, and she actually was at UCSD when it first started, actually was in San Diego when she won the Nobel Prize. And so what happens is this, the differential equation, like I said, that we want to solve is too difficult to solve directly. We're actually crappy at solving, in general, we're crappy at solving partial differential equations or any sort of coupled differential equations. We really can only solve 1D differential equations. We're good at that, and everything else that we really suck. So what we do is we can say, well, we can solve some 1D differential equation. And what we do from that is we get a set of what we call one-body states, one particle states. This is the function, basis function for a single coordinate or a single particle. And we label them by various quantum numbers that you don't have to worry about. And physicists have a special way of giving names to all of these that we love, and we dream about at night, and so forth. But the basic idea is by solving this simple differential equation, which could be a mean field or some other approximation, is you get a bunch of this idea of different wave functions, and they have a particular set of levels energies, and this is how we order and how we think about things. And again, it can be useful to understand it, but we're not going to have time to go into it in great detail here. But what we do is we create a basis state that's a product of these single particle wave functions. And we have to antisymmetrize it because they're fermions, but don't worry about that. And the technical term for this is a Slater determinant when we do the antisymmetry. And it turns out that because you have what's called indistinguishability, that is, you can't actually tell that this is particle 1 and this is particle 2, this one could be particle 2 and this one particle 1. All we really need to know is which one of these states are occupied. And so we actually can use something called an occupation representation, because these are fermions, and fermions all think they're special snowflakes. And so they all have to have some unique designation. And so what happens is that basically, if we label the single particle states 1, 2, 3, 4, 5, 6, 7, and so forth, you can either put one fermion there or no fermions. No fermions, one fermion, zero fermion, no fermion. And what you can then do is you can construct your basis states where you have where the fermions are occupying different one of these states. And in that case, it's literally just saying whether it's 1 or 0, which is beautiful for computers. You can really go to town with this for a computer. And this, by the way, helps to explain why the matrices are so sparse. The actual physical interactions can only move 2 or 3 of these particles around at a time. And so that means if you have more than 2 or 3, some of them have to stay fixed. They have to be spectators, and you basically just shift the action of the interaction just as is literally just shifting one from one place to another place. Now, there's one other thing you need to know when we talk about these things is an important thing about atomic nuclei, which doesn't occur in all systems. The system is independent of orientation. The politically correct thing to say is to say that it must be rotationally invariant. Now, the great mathematician Emmy Nether showed that if you have some sort of invariance in your problem, then you're going to have a conserved quantity. If it's rotationally invariant, then angular momentum is what's going to be is what's going to be conserved. And this is represented in quantum mechanics by a single quantum number. In this case, we give it the title J, and this is the magnitude of the angular momentum. Now, in classical mechanics, angular momentum actually has three components, X, Y, and Z. Quantum mechanics actually couldn't afford all three of those. And so in quantum mechanics, you get the magnitude and you get to choose just one of the components. By tradition, we choose a Z component, but you could choose something else. And so, but that also turns out to be a good quantum number. It's a conserved quantity. And we call this JZ, or sometimes just because we like to give things multiple names to confuse our students, we call it M. That stands for the magnetic quantum number because a magnetic field will pick out states of different JZ. So we have these two quantum numbers, J and M. Now, you can then choose which one of these quantum numbers you want to use to construct your basis. It turns out that as you go along continuum, you can make choices that will reduce the dimensions of your space, but they become increasingly complicated. So, for example, what I work in is called the M scheme, and these are basis states with total fixed JZ. The point here is that they're easy to construct with. Each one of these single particle states has a value of M, and the total M that you get for the whole state is basically just comes from just summing them up. And if you want to show off your group theory, like Eugene, the great mathematical physicist, Eugene Wigner, you understand that because the subgroup is a billion. And so you can do this. And this makes life really easy. And because I'm lazy, this is how my codes are mostly written, because it's really easy constructed. And so what we do is we choose just the basis states that have a particular M value that's fixed, and all of the ones we exclude. Now, you could do something different. You could have it with fixed total J rather than total JZ. This also has enforced rotational symmetry. It turns out it has smaller dimensions, but there's a price to pay. There's always a price to pay for something that you think might be improved. And in this particular case, what the thing is that is the price you pay is the states that have good total J are generally some linear combination of M scheme states. So that while the dimension may be smaller, the states that you have are actually more complicated. Now you can go further. If you're a groupie like Wigner or like many of my friends, you can choose other more complicated groups, things like SU3 and the symplectic group SP3R, which I can barely spell. And then you can just choose states from selected group irreps. And then you get some additional things, and they're even smaller dimensions, but these are also even more complicated. And not only that, but we can also understand it actually is not the total dimensionality that's the main computational burden. The real computational burden is the number of non-zero Hamiltonian matrix elements. Remember I told you that these matrices I'm working with are very, very sparse, like only one or two in a million are non-zero. And when you're solving the eigenvalue problem or doing matrix vector multiplication, that means is how many of these elements you have to find or have to store. And so that's the real computational burden. And we can compare this by looking at some cases where we look at different bases. This is for the exact same system. If we work in the M scheme, then the basis dimension is just about just under 600 million. It's almost a little more than half a billion. In the J scheme, what you do is you actually divide and conquer. You would do it for different values of J, each with a smaller matrix. And that's like an order of magnitude smaller. And you could go to some group like SU3 and you use all of them and you get an even order smaller magnitude in terms of the size of the vectors. And you would think, great, that's what we really want to do. And many of my friends do it. And then I point this out, which they themselves published in a paper, is this actually increases the number of non-zero matrix elements by orders of magnitude. So for example, like I said, the M scheme has the largest dimension, but the number of matrix elements is smallest, and it's still a lot of memory, but it's only 4 terabytes of memory. If you go to the J scheme, you need 200, it's almost 2 orders of magnitude larger. You need, basically 50 times as much memory. And even with this dramatically truncated group theory calculation, which is 2 orders of magnitude smaller in terms of the basis dimension, but it has almost 2 orders of magnitude more and it still has an order of magnitude more non-zero matrix elements. Still requires 4 times as much memory as the case. And so you have to, choose what is the issue you want to deal with. Also, these matrix elements, it turns out, are really easy to calculate. These are much harder to calculate because they're linear combinations of simpler things. So this is still a lot of memory. You still have 4 terabytes of memory. I have a very powerful workstation, but it still has only half a terabyte of memory. So you might say, are we always stuck running on a supercomputer? Well, not necessarily. There's always a way to go around this. And again, here you have to understand basically how your system is built. So we're going to use physics to think about this. Now, and not all problems will have this, but in physics, we have a bipartite system. We have 2 kinds of particles. We have protons and we have neutrons. And because in particular, because you usually have a fixed number of protons and a fixed number of neutrons, it's natural to write your basis states or basis elements as a simple tensor product. You're going to have some part of the wave function which is written in terms of protons, and which is another one's written in terms of neutrons. This turns out to lead to a tremendous savings because it turns out that many of these get reused, that many of these proton states will couple to many different of the neutron states. And so by this sort of factorization, we can really dramatically reduce what we need. So here's, again, some example of some nuclei, and these are the basis dimensions all the way from 640 to just over 1 billion. But if you just wrote it in terms of the components of the tensor product, then you need far fewer. Here you would need basically, for this dimension billion case, you would really need just about 126,000 the proton states, and because there's equal number of protons and neutrons, here you happen to need the equal number of neutron components. You get kind of a block diagonal form because this has to do with, again, conserving that m quantum number, which is not that important. But the point is that you naturally get a way of saving a lot of memory. You basically only, if you imagine all these interiors, these areas represent all these basis states, these 1 billion basis states. But all you really need to do is to store these along the perimeter and then have a fairly simple rule for combining them in here. And that's actually turned out to be really easy to write. So this is how we work. So this is one way you can sort of compress or factorize without loss some of your data. Now, it turns out that you can do the same thing to factorize the matrix elements for a tremendous saving. I won't have time because Dr. Shan said that they're going to have lots of questions for me. So I don't have time to go into all the details of this. Just to sort of say, it uses the fact that only 2 or 3 particles at a time interact, and you can loop over the spectators. And so this allows you to sort of factorize it. And there's I didn't invent this, but I did write a paper about this about 8 years ago, which people cite. And then here's the memory savings and factorization. So this is how much, this column right here, where it says matrix storage, is how much memory it would be to just store the non-zero matrix elements. The column of factorization is how much memory it requires to store them using this factorization algorithm. And you can see we save, at least 1, 2, or 3 orders of magnitude in memory. Something that would be huge any other place you can store with just a few of this. So like, for example, this lithium-7 case, a dimension of 252 million, it would take you 30, basically 3.6 terabytes to store the matrix elements, and I can do it in under 100 gigabytes. And I can run that on a powerful supercomputer. I mean, a powerful desktop workstation. So that's a tremendous savings. Now, we have used the same proton-neutron factorization to build J-scheme code. My PhD student, Oliver Gordon is doing this. And here the trick is to not use all of the J-scheme bases, but just to find the most important ones. The basic idea is we have a code, and we basically find some many proton states, and we do the same for many neutron states, and then we couple them together. And this is our J-scheme code. And the key here is we don't take all of the ones from the proton space or all of the ones for neutron states, but we take linear combinations that are lowest in energy. And this actually seems to work pretty well. Here's an example this full CI is solving in the full space. And in this particular case, the actual full dimension basis is about 2 million. And to do that, you need about 4,800, almost 5,000 of the proton states and the neutron states to construct it. But Oliver, using just 250 of each of those, got extremely good approximation to the full spectrum. And this is just a different calculation to sort of give a sense of scale. So although this one's actually even easier to do. So this is quite an advantage. And here's another calculation. This is for doing nickel 60. This is the M scheme dimension would be 1 billion to do. I could barely squeeze this out on a very powerful workstation, but on a laptop, Oliver was able to do this. And you can see if we basically increase the number of states we're using our calculation, there's a maximum number of about 12,000 of the proton many-body states, but using a small fraction of them, of just a few hundred, you get a very good approximation to the ground state energy. And we're going to be writing this up soon. And this looks like a very promising technique. Okay, I've been going a little bit fast, and I apologize for that. Let me also just finish. The last topic I want to talk about is computer architecture. And here it's useful to understand how computers actually work. So this Lanchus with this on-the-fly reconstruction, this factorization, is pretty efficient. But there's still a couple of things that you might want to be better. If you actually compare the time that takes compared to the ones that store the matrix elements, it takes about 2 to 4 times longer, just because you do have to do a little bit of algebra to reconstruct these things. Our setup time is actually much faster, so it almost balances out, but the time to do the matrix vector multiplication is on the order of 2 to 4 times longer. More worrisome is when we run these on a large job on a parallel supercomputer. That's where we distribute the work across many processors. We have some difficulty in load balancing, and we've spent a lot of time trying to do this. I've been working on it. Another student, Jordan Fox, has tried to work on this. And here's what the code does. Our basic workhorse, as we said, is basically we divide up the works of matrix vector multiplication. So that's our basic thing that we're doing. And what we do is we divide up. So we assign, say, each one of these squares to some processor or some set of processors to do this. And so we assign some processor to do the work. And we actually know how, well, in principle, we know how to do this efficiently. But in practice, it turns out that inefficiencies still remain. Some compute nodes will take twice as much to work as others. Even when we've done a lot of very careful study and try to model it, we have these imbalances. And I'm pretty sure we understand the reason why. It really has to do with something called data locality. And this is worth understanding about. So let me review where a computer stores its memory. Of course, you have the hard drive, the permanent memory that you have, whether it's a magnetic disk or a solid state disk. But of course, that's far away from the CPU and it's slow. Even a solid state disk is slow because it's far away. Then you have the RAM memory, which is on the same motherboard, but it's still physically different. And it's a little bit farther away from the chip. But then you have what's called the on-chip cache. This is a smaller amount of memory that you can store memory on, that the program accesses immediately. So it basically has memory very readily at hand, and you can access that fastest, but it's the smallest amount of memory that you can have. So you get you can get, terabytes of memory here. You're going to get, you can get up to tens of gigabytes in RAM, and then you're on the order of tens of megabytes on your cache. Now, what you have to understand is the way modern computers work is when you fetch memory from RAM, modern chips will grab nearby memory and they'll store it in the cache. So let's suppose here's a particular data that you need to go, at some particular address. what the chip will do is it will grab a bunch of, it'll grab a bunch of data nearby it. It'll grab a bunch of data nearby it, and it'll just plop it on the chip, on the cache, assuming that if it's nearby, I may need it. And that actually has improved chip performance, but it only helps if the next data you want is nearby. And the word you would use is local, as in data locality. I don't know that John von Neumann actually worked on that, but computer giant, all that stuff. However, in sparse matrix vector multiplication, data locality can be hard to come by. So let me point this out. Let's suppose that you locate this particular element in memory, matrix element, and it's multiplying this matrix element and produces this one. Well, because the matrix is sparse, the next one may be farther away, and it could be quite some distance on this vector. Now, there's a bunch of elements in here, but when you're looping through the non-zero matrix elements, you may be jumping around on the vector. And so this violates data locality, at least along one or both of the vectors. And so this loss of data locality makes it hard to balance the work because some data is more local than others. So to show you an example, here's an actual picture of basically the locations of the non-zeros on a particular matrix. And you can actually see sort of a block structure. This is actually related to that block structure I showed you earlier, having to do with quantum numbers. But you can see, first of all, it's rather sparse, but you can also see that some places are denser than others, but then there's these vast deserts. And so it's really hard to control exactly where the data is going to be local and not. So this is a problem. And after a lot of investigation, I've convinced myself this is the issue. Well, we can modify the Lanchus algorithm to try to deal with this. So what you do is, instead of matrix vector multiplication, is you're going to multiply blocks of vectors. So instead of just multiplying one vector to get another vector, you're going to multiply several vectors to get several vectors out. Now, this turns out to have several advantages. Like I said earlier, reconstructing this matrix element takes time. It's a lot of time, but it takes time. And so when you multiply, once you've gotten it and you apply it to multiple vectors, you're amortizing that cost. So that helps to reduce sort of the cost of the algorithm that recreates this factorized that you've got from factorization. The other thing that you get is that rather than storing the vectors column-wise, which would be the naive thing, you actually store them row-wise. So if you store the same element for several vectors all in a row, so that these are now local. And so now you get data locality back in. And then when you do all of this, you basically just modify the block, the Lanchus matrix, Lanchus algorithm, so that you're looking at blocks of vectors rather than regular vectors. So these things are now rectangular matrices. These are literally blocks of vectors. The columns are the vectors, although you store them row-wise. And then the tri-diagonal are now square matrices. But this actually doesn't really affect the performance at all. Now, with another PhD student, Ryan Smitkowski, we've coded this up and put it into my code, and it works fantastically. And Ryan's hard at work on the paper. And to show you this as a function of the block size, this is basically the number of vectors in a block. This is the time that it would take, and these are the number of vectors you're trying to keep at the end. If you run with just a single vector, it's basically independent of block size. You can see some fluctuations, and this just gives you a sense of sort of the fluctuations that sort of naturally occur in any run. But when we do block-wise, the equivalent amount of work goes down dramatically. It either more than half to, frankly, more than a quarter. So we get a tremendous speed up, and this is due to the combination of amortizing the cost and also getting much better data locality. To be honest, I'm not sure how much of each, and I don't really care. I got a factor of 4 speed up. Now, there is another issue that you have to worry about. Normally, when you do Lanchus, you start with a random pivot vector, and then the speed at which you get your multiple vectors, eigenvectors out is almost independent of that. There can be some variation, but it's not that different. When you do the same thing here, and you're starting from a pivot block, or you have a random pivot block, it turns out it requires more iterations than standard Lanchus. And here I define the iteration as basically the number of times vectors get multiplied, so that you can basically count them up as being the same. And so this undercuts the speed up. And you can see this here. This is the number of iterations that you need as a function of block size. Here, the black with the circles is the number of iterations you need to get to some convergence criterion. This is where you want to keep 4 vectors, 8, 12, and 16. If you do it with a block Lanchus and just some random pivots, then it actually takes almost significantly longer, almost twice as many, well, not longer, it takes almost twice as many iterations that you need to do. And so that undercuts a little bit of the efficiency. However, we can do something that we call bootstrapping. And some other people seem to do this. I haven't found any papers on it, but it's kind of known. It's one of those lore things that you just talk to people at conferences and stuff. We used to see people in person at conferences. What you do is your pivot block is actually an approximation. You solve the same problem, but in a high truncated space. And so that it already approximated. And it turns out that speeds it up remarkably. Here's 3 different cases that we've got this of different truncations. And even the largest truncation is, the full space is 6 million. This was just a small case. This is a tiny case, but just because it was easy for Ryan to do some simulation, run multiple runs. If you start with some starting vector that was done in a space that's only 10% of the full space, you can see that you need just a fraction of the number of iterations, even compared to the original Lanchus, less than half. And you can, even if you do even smaller truncations, then you still get a tremendous speed up, even if this factor of only 2,000 out of 6 million. You know, that's basically 1 in 3,000. 1/3000 is the size of it, and you still get at least somewhat of a speed up compared to ordinary Lanchus. Now, when you then add in this natural speed up from those other things, that the amortization of costs and the data locality, then your time to solution just drops dramatically. Even with a random pivot, block Lanchus gets a time to solution. This is running the code through everything, significantly reduces it by more than 1/3, almost half. When you use this bootstrap, it just drops like a rock. You can see that we're basically using less than 1/4 of the time, almost 1/5 of the time, to get to solution, which is, you know, a great thing. Particularly, you know, if it's a difference between 5 million hours on a supercomputer, just 1 million hours, that's not nothing. And most of the work is in the matrix multiplication. There's some additional work through the reorthogonalization, and reducing the number of iterations helps that, and so forth. So this is a fantastic advantage. And like I said, Ryan is currently writing this up for publication. And here's just another example of a slightly different case. It's a structured differently, it's a different dimensionality, but we see basically the same thing. The time to solution is improved here. The random pivot block Lanchus is outperformed by ordinary Lanchus. But once we start doing bootstrapping, particularly for some modest size truncations, then you really see that you can get a much faster time to solution. And the time in matrix multiplication is also improved dramatically. So this is a strategy that one can use. Now, while the Lanchus algorithm looked impressive, often I hear people say, oh, but I read this paper about some other algorithm and they say it's better than Lanchus. You know, why don't you use that one? Well, like many things, these algorithms have come and gone. Long experience shows the robustness and some utility and simplicity of the Lanchus algorithm. And it turns out that when you try to implement these particular alternatives, they often have some hidden requirement that don't apply in many cases. And I will fully admit, some of the tricks I've been using may not apply in all the cases that you have. But for example, at Lawrence Berkeley Lab, the applied math group was all hot on this thing that they said was much better. But it turned out that it required finding a preconditioner matrix. And a preconditioner, if you don't know, is a matrix that helps with gradient descent. It basically makes the gradient descent more even in conjugate gradient methods in an optimization problem. And all they could prove that if you could find the preconditioner, it would run better, but you didn't have any particular, you had to basically guess your preconditioner. Now they found cases where you could guess a preconditioner and it worked well, but in other cases, it turned out for us in our code, we couldn't find one that worked well. So, you know, I'm dubious now about other alternatives. The best variant, I will mention this briefly, and you can, you know, just go to Google Scholar and you can find all these papers. Something called thick restart Lanchus. This is if you can't store a lot of vectors in memory. This requires less memory for the Lanchus vectors, which it also saves on the reorthogonalization. But like with anything, there's a price to pay, so you have to ultimately do more iterations. So this is the next best alternative. And in some cases, I do use it for very, very large problems where I can't do hundreds of iterations. I may only be able to do 50. I will use thick restart. Okay. Sam said there are going to be lots of questions. So he asked me to talk fast. No, it's my fault, but he wanted me finished in 45 minutes, so I'm doing that. So this our lessons learned. You really can find some eigenvalues of huge matrices, but for the best performance, don't think in black box algorithms. Understanding the problem can lead to better ideas. Now, what I do for all my cases may or may not apply to what you're doing, but certainly some things may inspire you to think better. And it's important to understand not all ideas will work on all problems. So think and understand the problem, be modeled. And again, I think this is one of the great advantages of this interdisciplinary computational science program, because it teaches you to think about the science as well as the computing. But also simple can ultimately be faster even if it's bigger. And if you understand how a computer works, then that can lead to better algorithms. So let me just finish with ending with an advertising. Just like on YouTube or many other things, you have to watch a commercial. So here's the commercial for the course. I taught last fall, and I'm going to teach again this fall on quantum computing. All you really need to know are linear algebra. If you know eigenvalue problems, you're all set, and complex numbers. So with that, I'll stop and take any questions that you have. I know there were some in chat.
Thank you, thank you. This is great. This is a great talk. Very useful.
Yeah, and Josh said that this is definitely in standard textbooks like Matrix Computations by Golub and Van Loan and many other ones.
Wonderful computational CSRC talk, computation. You hit it. So questions, I bet a lot of questions. I do have a bunch. So, but anyway, questions for Professor Kevin Johnson. Okay, maybe I get started then.
Sure.
So could you show us a few examples of your, the results of your calculation of Binning order metrics? Like show us a pre-plot, the eigenvalue, decrease, increase, accumulation, percentage of variance explained, etc.
I mean, I can run an example on just in real time and show you how fast it runs. I don't know if that would be helpful or not. Even we don't. So what would you like to see again?
It's eigenvalues. You say the first 10 eigenvalues you have computed from a large matrix, and you just show us a.
Sure. Let me just bring up a particular.
First one will be the largest. Second one will be small, smaller, etc.
Yeah. So let me
examples of that.
Let's just see.
Give us kind of a flavor. What do you do? And
okay, so I'm going. Let's see. I'm going to have to make this even larger so that you can see it. Let me share screen again. Okay. Can you see this?
Yes. Yes, we can see that.
Okay. So I'm going to run my code. And don't worry about the various things. Let's just do. So this is a problem. This is a really tiny problem. This is a dimension 93,000. And let's do 10 eigenstates. And so these each time is doing 10 iterations. And so now there in 31 seconds, you get the lowest 10 eigenvalue. These are the eigenvalues. These are the excitation energies relative to the ground state. These are the angular momenta and some other things. And so it can run that in 31 seconds. And we could probably, I can actually set up to do something else in just a second. 20. So now I can show you to do 20 eigenvalues. And what you can see here, this is the eigenvalues. You can see them starting to converge. These have already converged, and they're okay. There that ran even faster because I actually had pre-calculated something. So it did 20 eigenvalues in 13 seconds. Mm-hmm. And we could, you know, one can do more. One can do even more. And I have all the wave function vectors, and I can do various analysis with them, and you know, calculate various things that I need from the vectors, and post-process them or in that code and stuff like that.
Okay. Then well, I want other people to ask questions. If you know, if I don't hear any questions, I take advantage of this time.
Okay, so there is a question: how to select the dependence of target selected eigenvectors on the size of the matrix? Well, so in physical conditions, you know, in my field anyway, we usually just want typically something like 5 or 10 of the lowest eigenvectors. It doesn't eigenpairs. It depends on the exact physics question you want to know, the exact science question. Sometimes you might just need 2 or 3. Sometimes you might need 50. But more often it's between 5 and 10, independent of the size of the matrix. That's just because what you have physical data for. Ill conditioning really isn't a big issue for us. The only thing that could be an issue, which may be related to that, is the density of states near the extremes. So states that are far apart near the extremes will converge faster. If they're very dense near the extremes, then they'll converge slower. So it's not so much the ill conditioning of the matrix as a whole, it's the separation between the extremal eigenvalues that may be that. And yes, I see Wen Jian Chung has a question. Go ahead, unmute yourself.
Yeah, so I was just curious. So from a dynamical systems perspective, you know how they always, you want to try to find eigenvalues for a dynamical system. You're looking at like the largest one, right? So this method, even for like very large dynamical systems, would it be able to tell us like, you know, whether the system is stable or not based on the eigenvalues? Would it
probably, because, you know, stability is usually a question about whether, you know, how many are negative or something like that, right?
Well, it's the question of whether all of them are negative or if there are some that are larger than 0.
Okay, well, so then you can, but see, it looks for the extremal ones. So it will find the most negative, the most positive. So yeah, you can definitely use that, and actually pretty quickly, if you just set it up, say you want to find out if there's any positive eigenvalues, you could run pretty quickly and see, well, how much what's the largest eigenvalue rather than the lowest, what's the highest eigenvalue rather than the lowest. And so yes, you could probably find that extremely quickly with this kind of method.
Okay, that's useful.
Okay. Then you showed us 20 eigenvalues and 10 eigenvalues. I noticed that those eigenvalues decrease very slowly in the real physical system. Normally it goes down faster than that. So my question will be, how do you know your results are accurate? Do you have error estimation?
We haven't done a lot of it. I mean, it mostly has to do with round-off error, but by experience, you kind of know what the typical size of it when you do multiple runs or use a slightly different system. I mean, for us, there's the size of the physical measurement. So let me just show. There's a couple of things. One, but also, let me say for our particular case. Let me just share the screen. We actually know that the errors on these numbers, due to the underlying theory, is usually on the order of like, this first decimal place. And that just has to do with the errors of how well we can do the theory, and that's independent of the algorithm. So we are usually good out to at least three and often 4 or 5 decimal places in terms of the algorithm, but we've not done a careful error analysis. But in a physical thing, you actually know that the phenomenology of your calculation really isn't going to be good then. Basically, the 1 or 2 decimal places. You're actually much better than that, but the point is you can't actually get better at being with the experiment than that.
Any questions from
which doesn't really satisfy you, I understand, but
well, we can talk more, but that's good to know about what you have already.
Yeah. So one thing that's relevant to that, which is interesting, is what precision do you need for doing various calculations? So, for example, we store the matrix elements in single precision.
Yeah.
When we calculate overlaps like dot products, we have to do double precision. But for matrix vector multiplication, single precision is good enough because it's so sparse. You don't add up enough of them. But when you do a dot product, because there's so many of them, you need to do double precision. But you're just keeping store of that. So we pay attention to all those things. And for our purposes, that works well. For some other problem, you might need to do double precision for it, but that would depend upon the problem.
We have a question in the chat.
So are you reading your large sparse matrix row-wise and not all at once? To be perfectly honest, it jumps around a lot because of the way that the factorization algorithm works. It actually is not in a particular sequence. So it actually jumps around a lot. And that's part of the reason why we need to, why the block Lanchus works well. But you're right, we actually don't read in the matrix at all. We just look at one matrix element at a time. So let me just hold this up as an example, just so you can see this. Let me share. So literally, it loops through and it calculates this matrix element and applies it and gets that. Then it throws it away. Then it basically calculates the next one, applies it and throws it away. I think I did that up here. So we never have a large fraction of the matrix in memory at any one given time. It's literally called on the fly. You only have one matrix element that you're dealing with at a time. And the reason is because it's such a sparse matrix, there's no benefit to taking chunks of the matrix at a time because most of that could be 0. I don't know if that helps answer your question or not.
But following that question, that is the issue we encounter is that, say you have your data here in your lab, say 2 terabytes of data. Doesn't matter what supercomputer you can use, suppose somewhere in Washington or somewhere in Colorado. But you have to read the data into that supercomputer. How would you do that in and out process for that huge data set?
Well, so what happens is these matrices, even if you're storing the matrix elements, like I said, we never store them. We never store them. We never store the entire matrix. We only recalculate on the fly all the time. And even those codes that store it, they have to calculate them one by one and populate it internally. So they have and actually they borrow some of my techniques to do that more efficiently. So when they're populating the non-zero matrix elements, they're actually doing that internally. They're not reading that whole thing from file. There's some seed data which explodes into that. So that you need. And to be honest, I could talk about that. There's many different layers of data, and actually, if you were to look at the matrix, much of it's repeated. Many of the numbers are used over and over again. It has to do with these spectators and so forth like this. And so there's actually a lot of duplication of our particular matrices. Now that may not be the case for everybody's problem, but for our problem, if you actually look at it, there's a lot of duplication for that. And so the factorization, the on the fly actually takes advantage of that, that you don't actually need to store all of that data. Now that may not be the case for many other people's problems.
Okay. Again, I have many questions, but other people give other people opportunity to ask. And this is also running late, and this is so interesting.
Looks like it looks like Wen has another. Wen, do you have another question?
Pardon me? Oh, I have a question, but I'll let other people ask their questions.
I don't know if Wen's hand's still up from last time, or if he has another question.
Yeah, I think it's still up from last time.
Okay.
Okay.
Any other questions? So then,
okay.
Go ahead.
Go ahead.
Okay. So with that, so it looked like your data is mainly model generated data. So that means if you use certain computer A, a supercomputer A is basically was generated. Suppose, do you have a problem that your data actually is from experiment, like say a experiment from CERN, and then you have to compute to do data process for this experimental data?
Well, the data, it ultimately is fitted to data. So our matrix elements that we read in at some level are derived from data at some level. And depending upon exactly the approach, it may be some few body system, or it may be some larger nucleus. And this is one of the big questions that we have. Now, we have actually looked at the sensitivity to our calculations to the fits to data. So one of my other students, Jordan Fox, has actually had a paper, and he's working on another one where he actually did a very careful uncertainty quantification of the fits of our matrices to the data. People had done the fits, but they'd never done the actual error analysis. So we actually had a paper basically last year that did a very careful analysis of this. It's a very good paper on how we did this. And so that's, we certainly look at that. We actually understand that better, because that's actually going to be bigger. That error is going to be bigger than any error from our algorithm itself for us.
Now, also a little from your experience of running such a large scale of computing, could you give us a little show of what kind of hardware you have in your lab or with your group, so that other groups can learn from you?
Well, like I said, part of the reason I wrote this code to be very flexible, so it will run on a laptop. I have a 32 processor workstation with half a terabyte, and then I run on supercomputers. I'm currently running stuff at Los Alamos and at Lawrence Berkeley Lab, and so the same code, different compile options, but the same code runs on everything from a laptop up to national lab supercomputers. And we can use OpenMP, we can use MPI, or we can use hybrid OpenMP, MPI, or it can run in serial. So we can run on a large range of platforms, and we carefully check against these different platforms.
So for that 32 processor workstation, 0.5 terabytes of RAM, what would be the current market value that you can buy?
Hopefully no one will try to steal it from my thing. It's probably about, I looked up about $8,000 or so.
Okay. And then another question would be, now for your big eigenvectors, and some of them I believe could be very useful for their physical meaning. So you may want to store a few of the eigenvectors. Each of them will be very big. Do you store some of the eigenvectors?
Yeah, we write those to disk, and those do take up large files. So at the end, so what happens in the code is all those Lanchus vectors are actually stored in RAM. So actually, that's for many cases, storing the Lanchus vectors, the Krylov space, actually takes up more memory than the matrix itself. So when I do 100 iterations or 200 iterations, I store those in RAM, and there I need a supercomputer to distribute those across that. If I don't have much memory, that's where I use that thick restart, because it requires fewer vectors, and so I don't need as much memory. And then at the end, though the converged eigenvectors get written to disk, and then I can post-process them. But those can be quite large. Those can be gigabytes of file, and often I have to write to my students to say, you've stored all your vectors and they filled up the disk. You need to delete some of them because I can't run anything, and so forth. And so there is a question if we're running it on parallel. The student, when he ran it on his laptop, I don't know about that particular version, but he certainly has been adding, he certainly has an OpenMP, and he's going to be adding MPI to the code. You're thinking about probably Oliver's stuff that I showed. He's actually improved the code a lot since the data I showed, and but we're adding parallelism to it all the time. My group is very interested in parallel programming. So, okay, so here's we have another question.
Yeah.
How do the basis functions affect the accuracy of the eigenvalue computations? Well, so here's an interesting question. Because we work in occupation, this thing called the occupation representation, even our input data assumes some sort of wave function. So while there is some, you can get a value that depends upon your choice of the eigenvalue. That's actually kind of external to running the code. It's just, for example, it just depends upon what you choose for your basis functions, and that affects the files, the values in the file that you input into the computer. So that can affect that final result. But in terms of how the algorithm itself runs, it's completely independent. And how do you determine what appropriate basis function to use? Well, you know, there are again sort of standard, there's standard lore about what people use. We tend to use the three-dimensional harmonic oscillators. But now we're with Ryan again, we have a project we're going to try to use something called natural orbitals, which comes out of quantum chemistry. And other people use this too, and we think it will make our results much more, they'll converge actually faster because we won't need to use as large of a model space. And so that's a project that Ryan's going to be working on.
Do you want to answer the next question from him?
I think I have answered all of them.
Okay, good. So yeah, do you you have a few students here. Do your students want to share their kind of experience with us, with other students? We have several other students here. I notice. Yeah,
I mean they mastered Lanchus and so forth. So if anyone wants to say anything, they can. But I know, you know, Oliver and Ryan have worked a lot on Lanchus algorithms. Jordan, I don't know if Jordan's here, but Jordan's worked a lot on, I don't see Jordan, but Jordan's worked on this uncertainty quantification of data. Stephanie's working on there's still some problems that even with these techniques, we can't do it using this method. And so Stephanie Lauber's working on some alternate techniques that may allow us to do a completely different kind of approximation, but in even larger spaces that we couldn't even, that would require dimensions of like 10 to the 15, which we can't even dream of. And so she's working on some techniques. So they all are working on various different aspects of this. And then there's a couple of students like Chris McBride and Mandy Bowman who are working on some quantum computing stuff. But those we can only really do tiny matrices right now.
So Oliver, do you have anything to add?
Hi there. I don't want to incriminate myself, but if there are any questions, I'd be happy to try to answer them.
Okay, any other questions? Oh, great. This is so wonderful. Kevin, you're doing really important work. You know, this is I know that engineering people, they routinely now encounters large matrices and their eigenvalue problems, and also, of course, the rectangular matrices and SVD problems. So this really is really helpful, stimulating, inspiring. So if not for any further question, last chance, last call. Okay, well, Andrew, anything you have? I know you. Great, good. Well, thanks a lot. So, Kevin, this is great. We will have a lot to discuss. Oliver, thank you very much for appearing here. And then,
Yeah, well, me and any of my students will be more than happy to discuss, you know, all things Lanchus and so forth. So
yes, that's nice. Good. Well, thank you very much. All have a good weekend.
Thanks, Colin.
Okay.
Fascinating talk.
Bye-bye.
thanks.